Hello, in this video we review our techniques of substitution and elimination and apply them to solve systems of linear equations in 3 variables. Let's get started. So recall that when you're solving a system of linear equations, meaning that each variable is only raised to the first power, no higher, we have one of 3 possibilities. The first was the case where the 2 lines, let's grab some color here, oops, sorry about that, where the 2 lines intersect in exactly one location. So for example, if we had a situation like this, we would say that our 2 lines are crossing in one place. There is one independent solution where the 2 lines are intersecting, and that was called a consistent system. We also had the situation, on the other hand, where the 2 lines never touched because the 2 lines were in fact parallel, and we had no solution. Then the third case was when we had 2 lines which were actually on top of each other, right? Those 2 lines were on top of each other, but we didn't realize it at first. And if you have 2 lines which are really the same line in disguise, we have infinitely many solutions where those 2 lines are meeting because they meet everywhere, at every single location. So with that in mind, graphically that's what's happening. Let's see how this would look, again, with substitution and elimination algebraically with our system. So suppose we have 2x plus 3y equals 6 and 4x plus 6y equals 30. Well, in that situation, we have 2 lines and we're really asking you, do these 2 lines ever intersect? And these 2 lines could be, for example, the cost for a business and the revenue for a business. And you might want to know, when will your cost and your revenue actually intersect? When will you break even if you're running a business? That's an important question, okay? If, for example, we had the second case here, where our cost was always above our revenue, this is not a good business venture. We would like for those to intersect at some point. So let's see what's happening in this contrived example. Well, to use substitution or elimination, I could begin by noting that I would want to eliminate either x or y. So I would need to first choose a variable to eliminate. So I'm going to approach it from the elimination perspective. If I chose to eliminate, for example, the variable, let's say x, what I would need to do is make a change by multiplying an entire equation by some number, except for 0, which would allow the x terms to cancel, meaning I would get one of them positive, like positive 4x, and one of them maybe negative 4x. In other words, I'm finding the least common multiple of the 2 coefficients, but making sure they end up with opposite signs. So for example, if you wanted to eliminate x, you would multiply by negative 2 in equation 1. And let's see what that would produce. Your new version of equation 1 would become negative 4x, 3 times negative 2 is negative 6y, and 6 times negative 2 is negative 12. That's the same equation that we had before, just multiplied by negative 2. So we haven't changed anything in what the equation is saying. It's just a different form of it. We also have our original equation 2, 4x plus 6y equals 30. Now with the elimination method, it's sometimes referred to as the addition method. And the reason is, the next step after figuring out your least common multiples, which you would like to cross out or cancel out, your next step is to add. You're adding like terms. So as you add like terms together, your x terms were designed to cancel. You built them that way. So let's see what that means for us here. Death to you, the x terms are gone. Now, we didn't actually plan on anything happening to the y terms, but the collateral damage here, it turned out, was that we ended up canceling the y terms as well. So we ended up with a 0 on the left side. We didn't plan that, but it happened. This is where a lot of my students get a little uncomfortable. They don't like it when x and y both disappear. They would prefer to just have x equals a number or y equals a number. They would prefer, in other words, this situation where your 2 lines are intersecting at exactly one location, one ordered pair. But this is actually one of the other 2 situations, right? Where the lines never touch or they always touch. Let's see which of those cases we have. Well, negative 12 and 30 need to be combined by addition, which would produce positive 18. That's right. At this location, when you get 0 equals 18, you have to ask yourself, is that true or false? And I hope you know the answer to that. That is definitely false. And if you get something false, what that is saying is there is no way for these 2 lines to ever intersect. In other words, these 2 lines must be parallel. So we have this situation where the lines never intersect, so there is no solution. So if this was your business venture, this is a bad idea, right? This would be the case where your cost maybe is always above your revenue. Not a good business venture. One way to write no solution, by the way, is the empty set, the braces with nothing inside of them. It's saying there is no x or y value which would satisfy both of them at the same time. Okay? Another way is to write the circle with the line through it. All right, well that hopefully is a review for you from previous math classes. But what we're going to do now is try to go a step beyond what you know from your old days of substitution elimination to just from 2 equations with 2 variables to now 3 equations with 3 unknowns. Now again, in real life you could have many constraints, not just 2 or 3, but we're going to focus right now on 3 to get our bearings, okay? So let's head over to our next slide. Now, visualizing this might be easier for some of you than others, but let's take a look at what this is saying. Suppose we have 3 equations with 3 unknowns. Now, those unknowns, those variables, could simply be written as x, y, and z. They could also be written in some textbooks with subscripts like x sub 1, x sub 2, x sub 3, and as many x sub whatevers you need for your variables that are unknown, okay? When we have a situation like this with 3 unknowns, visually what we're suggesting is instead of 3 lines, we have 3 planes. I like to think of planes as pieces of paper. So if you imagine a piece of paper, it has a certain x and y component that you could draw on, a certain y component going up and down and x going left and right. But it also has a certain thickness or depth, and that's what we refer to as our three-dimensional, third dimension, which is z. We use that z quantity here. So what we notice here in our display, we see that there are several possibilities here. The first possibility is the case most students prefer, and that again is that situation where we in fact have one place in space or 3-dimensional space where our 3 planes or our 3 constraints are all satisfied. It's kind of like if you have 2 other friends, this is the one area where you all agree, okay? It's the one place where all 3 of your perspectives come together, okay? So we really like that situation. That's our most comfortable situation when we have a point in 3 space where all 3 constraints are satisfied. Now, on the other hand, we often have a situation where the 3 planes can't be satisfied at the same time. The 3 conditions aren't able to be satisfied together. Now, that can look a couple different ways. One way is where all 3 planes are on they're on different planes. They're not going to intersect anywhere because they're parallel. If you have 3 parallel planes, we call that an inconsistent system because the 3 planes never touch each other, okay? But it doesn't even have to be that dramatic. It could just be the case that 2 of your planes intersect, but not all 3. And that's what's happening down here, where we have a plane that intersects with 1 plane at a time, but not all 3 together. The last possibility, though, that is a little interesting, in my opinion, is when we have all 3 planes coming together, but not at a single point. Instead, at a line. That's the situation where it is consistent, but in a dependent sort of way. Every single point along this line is a solution. Okay, so we have infinitely many points which are solutions in that scenario, but they're on a line. So how would we know which of those situations we have? Well, let's get started with an example. So suppose we have here our example of x plus y plus z has to equal 4. Y minus 2z must also equal 4. And z must equal -1. Now this type of situation with 3 equations and 3 unknowns is very special because it actually appears almost like a triangle. So we call this like triangular form. It's not quite a perfect triangle, but visually it almost appears to be that. In the sense that in the first equation we have 3 unknowns, in the second just 2, and in the third just 1. So it looks almost like a right triangle. The reason the right triangular form is helpful is because we can back substitute. From the third equation, we know that z is -1. If we back that into equation 2, let's see what we would have. We would have y minus 2 copies of z, where z is -1, is supposed to equal 4. If that's true, then that really is saying that y plus 2 must equal 4. In other words, y equals, that's right, 2. Well, now we have what z equals and what y equals. As soon as you start getting numerical solutions like x or y or z equals a number, you know that you're talking about the first situation here in our diagram. And that was a situation where we had one single place where all 3 planes are coming together. So we have one more variable to solve for now, and we can do that by back substituting our z and our y answers into equation 1. So let's do that. In equation 1, we were told that x plus y plus z must equal 4. So we don't know x, but we are sure that y should be 2, and that z should be -1. We were given that. And that when I add up the 3 variables, I should get 4. Well, that would mean that x plus 1 ends up equaling 4, and that's a nice, easy linear equation. X equals 3. So we've now done it. We've found the 3 variables that would satisfy this system of 3 constraints at the same time. So they would come together at one point in space, and that solution set would be the point when x is 3, when y is 2, and when z is -1. Notice the order does matter because our first, our second, and our third are referring to specific variables in space, specific coordinates. So 3 to the right, 2 up, and 1 out, but in the opposite direction. Okay? All right, so we've now shown you how we could use basic substitution, backing up into previous equations, to solve systems of equations in 3 variables. Okay? But it's not always going to be that nice. We're not always going to give you a situation like this in triangular form. So let's take a look at a harder case and see how we would go about it. So in our next example, you can see we have 2x plus y equals 4. We have x plus 2z equals 3. And we have 3y minus z equals 5. So the triangular form is not present. But what could I do? Well, if you think back to the easier example that we started with today, we're always going to look for substitution or elimination whenever possible. But there are a few things which we are always allowed to do in that process. Now, the process that I'm about to describe is something known as Gaussian elimination. Gauss was a mathematician who discovered this process. The things that he discovered were that there were 3 operations that we could do in any order as many times as we need to until we have completely solved for our system. And these 3 row operations, rows instead of equations, like row 1, row 2, row 3, include we're always allowed to switch rows. We're allowed to switch the order of the equations. Doesn't make any difference which one you write on top or bottom or in the middle. Secondly, we're always allowed to multiply a row or an equation by a number called a constant, as long as that constant is not 0. Now, right now, there's nothing in your mind that would make you want to multiply an equation by 0. I think you would realize that that would kill an entire constraint, and we're not allowed to do that. But I promise, when we get into our next set of videos, as we start talking about matrices in particular, one of the things you're going to be wanting to do is to get 0 in certain locations. And multiplying by 0 will be a temptation for that. So watch out, you can never multiply a row by 0. Finally, we are allowed to add multiples of rows together. We've done that before. In the very first example today, we multiplied equation 1, I believe, by -2. Always allowed to do that and then add those equations together. Okay, so how would I use these row operations to help solve this system? Let's take a look. One thing I could do is, first of all, my first step, if you will, would be to choose a variable to eliminate. So which variable would you like to eliminate? On your own, you can feel free to pause this video and try it on your own. I would look at my system and I would see, well, what's already been eliminated for me? For example, in equation 1, there is no z. So if this were me, I might choose to eliminate the variable z. So I'm going to choose to eliminate z. You could choose x or y as long as you are consistent. So if I choose to eliminate z, here's what that would mean. Equation 1 already has that for me. So equation 1, I'll just copy. I already have 2x plus y is equal to 4. Let's take a look at how we could get another equation like this with z eliminated. Well, I noticed that if I looked at equation 2 and equation 3, I could almost add them together and eliminate the z, but I would first need to multiply equation 3 by a number. Can you think of what number I would need to multiply by? That's right, by 2. If you multiply equation 3 by 2, the new equation 3 would become 6y minus 2z is equal to 10. So that's my new equation 2. And now I could combine that with the old equation, sorry, that's the new equation 3. I could combine that with the old equation 2, which was above x plus 2z is equal to 3. And let's see what happens. Well, adding like terms carefully, the x and the y are not like terms, so we'll just copy that x. We'll drop down our 6y, and the z's do in fact cancel. Death to you, death to you. 10 plus 3 is 13, and now look what we have. We have a new equation which only has x and y, so we have eliminated z in a second equation. So we pick first a variable to eliminate. Since one of the equations already had z eliminated, I simply copied it. Now I'm going to bring up my new equation, my new equation here, which was x plus 6y equals 13. There's my new equation. And I can now perform either substitution or elimination on this new system of two equations with two unknowns. Notice they're the same letters, x and y. And we can get our answer that way. So after you perform your substitution, I'll make a note here, you're going to do that on your own because we've already gone over that once today. After you do your substitution or elimination on this system, you should be getting, let's take a look, for x, you should hit 1, x should be 1, and for y, you should be getting 2. Okay, so you'll try that on your own. If you need any help, go back to that previous example. We went through the problem just like it. Now, once you have x is equaling 1 and y equaling 2, you can then plug those numbers into any of the original three equations where we have a z present, because we are solving for z now. So the easiest one, in my opinion, is probably equation 3. So going back to equation 3 here, we had 3y minus z should equal 5. But we know what y should be. Y should be 2. So let's see what z would be. So 3 times 2 is 6. 6 minus z should equal 5. So if I move my variable and my numbers around, we do end up getting that z equals, that's right, z is 1. So my solution, again, is a simple point in three-dimensional space when x is 1, when y is 2, and when z is 1. You can always know you're right when you get a solution like this by simply plugging in those numbers into all three equations and making sure that they are in fact true. If not, if it fails in any of them, you have made a mistake somewhere. Okay, so again, what were my legal operations? I could switch rows, multiply rows by any number that's not 0, and add multiples of rows together. That will take some practice for sure, so make sure you definitely do take advantage of the homework problems I've suggested. Let's go on to our next slide. All right, so we're going to do an example now of how we can use our row operations to solve a system of equations with three variables. Let's do it. Okay, so we're looking at a system where we have three equations and three unknowns. It can seem overwhelming, but if we have a game plan, we're going to be okay. So the first thing we did, if you remember from our last example on the last slide, was we chose a variable to eliminate. So you have that freedom. You have the choice to eliminate any variable you want. I'm going to choose, in this case, z, but you could choose x or y. So I choose to eliminate z. Once you've made that choice, you would then work with two equations at a time to get z to go away, basically. So I'm going to choose equations, let's say 1. So if I copied equation 1 right now, I would have x minus 2y plus 3z equals 7. And equation 2, what would I need to multiply equation 2 by in order for z to go away? Let's think about that. Well, negative 3, exactly. So let's do that. Negative 3 times equation 2. So that new version of equation 2 would look like negative 6x, negative 3y, negative 3z equaling negative 12, right? When I combine my like terms, because that's what the elimination method does, you add your like terms at this step, I get negative 5x by adding, I get negative 5y by adding, and I notice that 3z cancels, death to you, death to you. 7 minus 12 gives me negative 5. So I have an equation now with just x and y. We did this in our last example, so hopefully this seems familiar to you. Now, if you're really paying attention and you like to work with easy numbers, you might notice that a negative 5 is pretty present in all three terms. So if you felt like dividing all three terms by negative 5 and getting x plus y equals 1, feel free. It's the same thing. So you're always welcome to multiply or divide by a number that's not 0. Okay, I'm going to keep it the way it is because I'm a little lazy right now, but feel free to do that if you prefer. Next up, I need to come up with another equation with the same two letters, x and y. So I need to, again, eliminate z by putting two equations together. I already used equation 1 and 2. Maybe I'll use equation 2 and 3. That looks pretty helpful to me. Looking at equation 3, just the way it stands right now, I have negative 3x plus 2y minus 2z equals negative 10. Okay? Now I want to put that with one of the other equations so that z cancels. How about equation 2? Well, what would I need to multiply equation 2 by in order for z to eliminate? Last time we did negative 3. This time, what would it need to be? Think about it. That's right, positive 2. If I multiplied equation 2 by positive 2, the new version of equation 2 becomes 4x plus 2y plus 2z equals 8. Now combining those equations, that system becomes positive 1x plus 4y, the z's cancel, death to you, and 8 minus 10 is negative 2. Well, now you have a system of equations with just two variables, x and y. So you could stack them underneath each other, on top of each other, however you like to write it, as long as you know what to do next. Now this is just like the first two examples that we did, where you have a system with two equations and two unknowns. You either use substitution or elimination to solve for x and y. I'll let you try that on your own. Feel free to pause the video at this point. And the answers that you should be getting is x should equal 2 and y should equal negative 1. So make sure you can get those answers. If you can't, you can always reach out to me and we could review that process. Okay, finally, once you have x and y, you need to plug them back into one of the original three equations. That's right. We're looking for z, so I'm going to pick one of the equations where z is not too difficult to get. To me, it looks like equation 2 is the easiest, but any 3 is okay. You're allowed to pick any 3. So if I plug in x, which was 2, I would have 2 times 2, because that's what the equation tells me to do, plus y, which is negative 1, plus z should equal 4. And when I solve that, I get 4 minus 1, which is 3. So I get 3 plus z should equal 4. So z is, that's right, 1. So my solution set would be the ordered triple when x is 2, when y is negative 1, and z is 1. That is the only time and space where those three planes are intersecting. So that's that one point where all three constraints are satisfied. So this is a consistent system with one independent solution. All right, so we've done a few examples, but definitely it's going to take you some time to practice and feel good about your skills here. They recommend to be able to do at least 3 in a row correctly without mistakes to feel like you've mastered a concept. So it's up to you now, because math is not a spectator sport. I'll see you next time.